All right, so we're going to start in chapter 6 talking about how to find the area between two curves. So get yourself ready for notes and we're going to get started. So finding the area between two curves, we see a picture of that over here, where we have a curve f of x and we have a curve g of x. And the area between this will always be given on some interval, or we'll have to find that interval ourselves in the problem. And we've got, in this case, from a to b. And here we see that f of x is over g of x, so we could just say this is area is equal to the integral of f of x minus g of x. If you don't want to go through the work of figuring out which one's the upper bound, which one's the lower bound, you can absolutely just put absolute values in here if you're typing it into your calculator. So, as long as there are no intersections on that interval, if you're using it, you can just find the absolute value. This can be a problem if you're doing it by hand. Your calculator will always handle it. If there were, let's say, an intersection in between A and B with this, and you were trying to do it by hand, you would have to split it up into two separate problems. But if you're on a calculator, you can just use the absolute value, which for most of you will go math, then click number, and then absolute value. You can type it right into your fnint function. However, we're going to be doing some stuff by hand. So, for number 1, it says, find the area between y equals 5x minus x squared and y equals x squared, bounded by the curves. So in this case, it doesn't give us a nice interval from a to b like we see in this picture. We're going to actually have to find it ourselves. And we're going to start by looking at the picture. And we have to find the intersection points. So the first curve is a quadratic. It's a downward facing parabola. And then we have a line going through the origin, y equals x. So we're looking for that area shaded in green. Now to find the intersection points, you can, if you again have a calculator, that's great. If you don't, to find the intersection points, is remember we set the two functions equal to each other. So when is the parabola equal to the line? And then you can solve using whatever method you like. I'm going to set it equal to 0 and factor. So I subtract x from both sides, and I get 4x minus x squared is equal to 0. When I factor, I then get x times 4 minus x equals 0. And so we have intersection points at x equals 0 and x equals 4, which makes sense looking at this picture. We have the one that goes through the origin, and then we have 4, 4 up here. And those will be our boundaries. And all we need are the x values, since we're going to write our integral from 0 to 4 in terms of x. In this case, we know that the quadratic is the upper bound. But what I'll show you is that if you just remember absolute value, you'll still get the correct answer. So even if you accidentally switch the order, so x minus 5x minus x squared dx, which I would first simplify from 0 to 4 as negative 4x plus x squared dx. When I integrate that, that would be negative 2x squared plus x cubed over 3, still on the bounds from 0 to 4. So I end up then plugging in that. We get negative 2 times 16 plus 64 over 3 plus, and then those are all going to be 0 terms. So since I'm plugging in 0 to a polynomial, so I'm not actually even going to worry about it. And when I evaluate that, I do end up with negative 20 over 3. You can say, oh no, I got a negative number. That's all right. It's the absolute value of that number. So this would be 20/3. So even if you have the bounds the other way, you end up with a negative. Just remember that you're using absolute value. Another trick that's really helpful with the area between curves is if you look at the picture, and especially true of things the sine and cosine, is that you're often going to have a lot of symmetry. So here it says find the area between sine, which is this curve right here, and cosine, which is this one, from 0 to 2 pi. I've shaded in and drawn things out here, and what I would hope that you'd realize is that this has symmetry this area here is the same as the other areas added together of these two combined. So instead of trying to write three separate integrals, one from 0 to pi over 4, one from pi over 4 to 3 pi over 4, and one from 3 pi over 4 to 2 pi, which is what you would have to do by hand if you have intersection points in a range, if you aren't allowed to use your calculator in absolute value. In this case, I would just as easily say, well, this is 2 times the integral from pi over 4 to 3 pi over 4, and in this case, sine is the upper bound minus cosine, the lower bound d theta, and that's going to equal the entire area from 0 to 2 pi. So often sketching it out like this is going to be very helpful. Then we're going to integrate it. You get 2 times negative cosine of theta minus sine of theta. Be really careful with your negatives when you're integrating and differentiating with trig. From pi over 4 to 3 pi over 4, like so. And then when you plug in your values, you end up with 2 times negative cosine of 3 pi over 4 minus sine of 3 pi over 4 plus cosine of 3 pi over 4 minus a negative, so plus sine of 3 pi over 4. Whoop. I just adding the 3's again. Just regular pi over 4. If you remember, all the pi's over 4 are going to be on the unit circle as root 2 over 2 plus or minus. 3 pi over 4 is here. So you've got a negative cosine, a positive sine. And then here they're both positive, and they're going to be root 2 over 2. So 2, then in this case, times negative, negative, so positive root 2 over 2, minus root 2 over 2, plus cosine root 2 over 2, plus sine root 2 over 2. These cancel out. This becomes 2 root 2 over 2. 2 times 2 root 2 over 2. So our final answer is 2 root 2. Review your unit circle. It's going to be really helpful for you in a lot of these different problems that you aren't allowed to use a calculator on. If you have any questions about area between two curves, please be sure to reach out and set up a Zoom call. Leave something in the comments and I'll get back to you as soon as I can.